Hey there guys, welcome back to a new video. Today we are going to be following on from our differentiating skills of polynomials, and I'm going to be introducing you guys to critical points. So let's get straight into it. So in the last video we looked at the function ax squared plus bx plus c. If you don't know this, this is the quadratic form for a polynomial with degree 2. And if you don't know, the root of this is x is equal to minus b plus minus the square root of b squared minus 4ac divided by 2a. Now, we're not going to be proving this directly today because that's more of an algebraic proof, and I will do a video on that in my algebra series later on. But today, what I'm going to be doing is I'm going to be showing you guys how to find the what we call critical point where the derivative is equal to 0. And we call this the vertex in algebra. So let's go ahead and let's find it. So f of x is equal to ax squared plus bx plus c. Okay, in the last video we introduced ourselves to the power rule. So that would mean that f prime of x using these rules is equal to 2a x plus b, correct? Okay, so as I said, we're setting the derivative equal to 0, so let me make a note here. When f prime of x is equal to 0, we have a critical point. We have a critical point. Now, later on we'll determine the nature of this and how to determine the nature. I'll show you guys how to, and you'll see some very interesting things occur there. So let's go ahead and apply this. So f prime of x is equal to 0. So we need 2ax plus b to equal 0. And now all we need is some simple algebra skills to finish this off. So we can move b over to the other side by taking away b on both sides, so subtracting b on both sides. So 2ax is equal to minus b. And now we can rearrange for x by dividing by 2a, because a is just some constant. So x is equal to minus b over 2a. And if you don't know this, a cannot equal 0. And that follows this, our definition here, because if a is 0, then we just have a linear function. If a is 0, only linear. And hence a vertex is actually not possible. Okay? So this is our definition to find the vertex of some polynomial. So let's go ahead and put up a random example. F of x is equal to 3x squared plus 6x, my x is a bit different, minus 3. And you can see there's no c here. So in our definition for the vertex, there's no c. It's because the derivative of a constant is always 0. So we only have to consider these two constants here, 3 and 6. Okay, let's go ahead and do that. So from our form, sorry, the keyboard keeps coming up for some reason, but what can you do? So in our form, AB, so our A would be 3 and B would be 6. So all we have to do is go that x is equal to minus 6 over 2 multiplied by 3. And by chance, our vertex is at minus 1, because that is minus 6 over 6, which is minus 1. Okay? And let's throw up another example. F of x is equal to ax squared plus a plus a. Ax, that is. Ax. And you might be thinking, okay, this is interesting. We have all the same constants, okay. So by definition, we use our definition, a minus b is equal to a, okay. Wait, minus b is equal to minus a, sorry. Minus a is equal to minus a. Minus b is equal to minus a, so our a is equal to a, so x is equal to minus a over 2a, and that is the same as minus a half. Okay, so when the constants are always the same, then our vertex is at minus a half. So let me go ahead and bring up Desmos for me to show you guys that. Desmos.com. And let's chuck in a random polynomial that has all the same constants. Actually, we can put up a polynomial with a. So x squared, oh, for some reason that keeps happening, x squared plus ax plus a, and let me add a slider here. So here we have minus half. See that? So if I go back here, we've got minus a half. Okay, that's good. So if I change my a, you can see it's consistently a half. See how the vertex isn't moving? Quite interesting, isn't it? Never moving. And let's see what happens as a equals 0. Okay, interesting, right? There's no vertex, so our definition doesn't apply. But for all a, but a is equal to 0, we have that. Okay? So, pretty good stuff there. So, how about an example where we are not using this form, where we have a higher order? So, for example, f of x is equal to x cubed minus x. Well, in this case, we can't use that definition to find a critical point or a vertex because it's a completely different type of function. A different type of function, I should say. So f prime of x in this point, we know from our definition, is equal to 3x squared minus 1. Okay, now if I want to find a critical point, I have to set this equal to 0. So I go 3x squared minus 1 is equal to 0. Let me bring it up here. And now we rearrange. 3x squared is equal to 1. Okay, now we divide both sides by 3. X squared is equal to 1/3. Okay, and x is equal to plus or minus 1 over root 3. So that would be our critical point right there. What does it look like? I'll show you guys in the next video.